This conference will now be recorded.
Good morning, everyone, and welcome you to the last day of this student development program. So today we will discuss about the critical analysis for desired poles for the pole placement controller. Bundy, Arun, Deep, please on mute.
ఏది తెనాలి కాదు తెనాలి టెంపుల్ సిటీ కాదు
Aparo, could you please be on mute?
సార్ సారీ సార్
So today we will discuss about the critical analysis for desired poles and the pole placement controller. Though our actual plan was to discuss about the single machine infinite bus system, which I will discuss briefly at the end of this lecture. However, I feel this is very much important as far as the participants are concerned. They have requested in the feedback as well as in the personal chat as well that they would like to know something more about the pole placement controller, how to place the poles and so on. I was thinking that this is quite fundamental and one can easily can gain this knowledge by reading the books, but I think it is the need of the hour as far as the participants' perspective. So today we will be discussing about how to choose the desired poles. The fundamental things what I was yelling from the past 4 days is that the poles, if we are keeping farther away from the imaginary axis, the faster it will be. And but today we will do the critical analysis with the different examples, and you have to also support me in doing some simulations, which I will tell you what to do and so on. So let's start our discussions on the critical analysis for the pole placement controller. And myself is Bharini Chandrakumar, and I am an academic at GMR Institute of Technology. So this is the last day, day 5 of the unique hands-on SDP student development program on control system design from a beginner to an expert, SDP 1.2. So this is the recap of the last 4 days. We have started our journey with asking the fundamental questions of why the control system is required and what are the applications. And then we have started with a simple, without even going into the details of PID, we have seen the gain proportional controller and the necessity of the closed loop control. And then we have seen the PID control of a simple system, which was, we will see what is that particular system is. And where we have seen how to design the PID gains by using various methods. One is the trial and error methods based upon thumb rules. And the second one is by using the auto tuning method. And then we have seen the open loop analysis of DC motor and buck converter and their PID control designs as well. And further, we have explored the pole placement controller for DC motor and the buck converter as well. And as far as the buck converter is concerned, we have seen two different approaches. One is for the simple transfer function approach, where we have tried to derive from the state space model, the transfer function, and from there, rather than using the standard transfer function, we have replaced it with some kind of realistic switches, the MOSFET for the actual switch, and the diodes and inductor, capacitor, and the resistors, load resistance accordingly, which is bit close to the realistic scenario. And then we have seen how to design the controller. Without controller, the duty cycle was one such parameter. Is only the control which was controlling the output voltage, and and we have seen how to design the PID controller to achieve the desired voltage, step down voltage. The similar thing one can extend it for the boost converter or the buck boost converter as well in a very easy way. So since I will again go from the very fundamental things, please don't mind in listening this very fundamental things, because this is very much important. From these fundamentals only we have gained the knowledge how to design the desired poles for a pole placement controller. Since most of you have asked, I don't have any other option. I will go with the very fundamental things, and from here we will see how we will go for the pole placement controller. All of you listen this carefully. All of you please listen this carefully. Although this might look very simple things, but lots of hidden information is there in this particular content. So the desired pole selections for PPC. PPC means pole placement controller. And here we are restricting our discussion to only the second order systems, but the same can be extended to any order system as well. So this is the standard second order closed loop system, omega n square by s square plus 2 zeta omega ns plus omega n square. And if you see, this is the transfer function. This is the open loop transfer function. You can see that there is no this omega n square. You couldn't able to see the omega n square. But when I use the feedback control, when I use this feedback, and if I use g by 1 plus gh, this omega n square is coming to the picture. So the two parameters which completely dictates the system's performance, as we discussed earlier, are undamped natural frequency and the damping ratio. So undamped natural frequency of the second order system, which is the frequency of oscillations of the system without damping. We have seen for a practical systems, one can realize one can the undamped, if you want the sustained oscillations or undamped oscillations exactly. So what you have to do from the series RLC circuit, just remove the R component, which is the damping factor, and then you can able to find out what is the natural frequency of that one. So the next one is the damping ratio of the second order system, which is a measure of degree of the resistance to change in the system output. So we will not go much into details of this one. So this is the standard second order system, so which we have already seen. And the important thing here is these are the poles. Since this is a second order system, if I factorize, if I equate this denominator equal to 0, and then if I start factorizing, I will be getting two poles. You can see that one is plus and another is minus here. So two terms are getting added here, and the same two terms are getting subtracted here. So you can see here what exactly based upon these zeta values and the omega values, you can get the different types of responses. So that's what I'm saying. So based upon the zeta value, one can be said there could be four different categories. One category is overdamped. So when can I say a particular system is overdamped? If the damping is greater than 0. Greater than 1. If the damping is greater than 1, then we call it as a overdamped. So the two poles, whatever we were seeing till now, the yesterday, the poles like -1000, -2000, -3000 will come under this category. So this minus A and minus B. So the poles will lie on the x-axis, on the real axis. And poles, both of them are negative. Then we call it as an overdamped system. And where the zeta is greater than 1. And the second case, the poles again lie on the left half of our display. If the poles are complex poles or the imaginary poles, then we call it as an underdamped system. And this is only possible if the two conjugate poles, if you get between 0, if the damping ratio is between 0 and 1, we call it as an underdamped system. Most of the systems, whatever we generally derive the second order time domain specifications, we generally start with the underdamped system itself. And the undamped system, when the damping is zero, when the damping is zero, we call it as the system as undamped system. In that case, the poles lies on the imaginary axis. All these things can be easily can be explained from this term. From these terms, one can explain. So, for example, if I say that zeta equal to zero, if I substitute here, this real part of both the poles will become zero. And if you see this, zeta is zero, so minus one, which is nothing but root over minus one is j. So j omega n here, and the minus j omega n. So the real part is zero. So the only the imaginary part will be there, which is that the poles will be on the imaginary axis. We call it as an undamped system. That means there is no damping in the system. A physical example for this particular undamped system is an oscillator. Undamped means there is no damping, there will be sustained oscillation. And in the laboratory, whatever we are using the function generator through which we generate the kind of sinusoid signal can be treated as an undamped system, where there is no damping. Continuously, it will be sustained oscillation. And the critically damped system, if both the poles are lie on the left half of a plane and they are repeating pole. If they are repeating pole, we call it as a critically damped system. And in that case, two real poles but equal poles, zeta equal to 1. If I substitute zeta equal to 1, if you see here, then what is going to happen? This element will become 0. Similarly here also. And hence you will be having the only the poles at minus omega and zeta, sorry, minus omega n, because zeta equal to 1, and minus omega n. So this, whatever you are seeing minus a, is nothing but minus omega n for this particular case. So this is called as a critically damped case. So there are 4 different cases: overdamped, underdamped, undamped, and critically damped. And these, by seeing just the pole locations, you can tell which kind of it falls under which kind of damping system. It is quite easy to do that one. And one thing, if you observe, if you have the pole on the right half of a plane, then the system will become unstable, and all those properties what we are going to discuss will not be applicable. Will not be applicable in settling time, rise time. Nothing will be available because the system is continuously increasing exponentially or linearly. It is continuously, becoming. If the system is unstable, then it is completely growing. So, bounded input, bounded output. So, even though the input it is also bounded, the output will not be bounded. So, you cannot able to find out this time domain specifications. So, this is very, very much important. Now we will see the if how to use the concepts whatever we have learned till now. And this is the classical underdamped response, underdamped system response. So that means zero lies between zeta lies between 0 and 1, and the natural frequency is greater than 0. Then you can see the same figure, the same plot I have already discussed in the very first or second class, which tells about what is time delay, delay time, peak overshoot, and peak time and settling time, and so on. I will not discuss it again. And these formulas are very much important. The rise time formula, pi minus beta by omega d, uh, peak time pi by omega d, and peak overshoot e to the power of minus pi zeta omega n by omega d. Omega d is root over 1 minus zeta square into omega n into pi, and the settling time this one. So now we will be focusing on only these two parameters. We will try to design the desired poles based upon this maximum overshoot or the peak overshoot and the settling time. So we assume that remaining will automatically will satisfy the design specification. So we are so only please remember this formula: mp equal to minus e to the power of minus pi zeta by root over 1 minus zeta square. If this omega, if you substitute from here, this is omega n. So you will be only be left over with e to the power of minus pi zeta by root over 1 minus zeta square. And the settling time is for the 2% only will be considered 4 by zeta omega n. Okay, So these two formula are very much important. Based upon these two formula only, we will derive the desired pole location. So the question what we should ask ourselves is, how do you use the concept of second order time domain specification to select the closed loop poles for pole placement controller? The closed loop poles here means desired poles. How do you select the desired poles? So in general, in the pole placement, what we are doing here is, the first thing is we are trying to first of all, we are trying to from the time domain specification, we will design or we will obtain the desired pole. So we want our system, the closed loop system, to follow or to behave the closed loop eigenvalues of the system should be the same as that of the desired pole. That means we are forcing our system response to behave very similar to that of the desired pole system. So desired pole, suppose if there are two poles, if they are desired minus A and minus B, then the desired system will be 1 by S plus A into S plus B. So whatever the second order system you have, we are trying to force in such a way that it should mimic the desired poles or the desired systems which has been made up through the from the desired poles. So the question is, how do you use the concept of second order time domain specification to select the poles for pole placement controller? So, so we will see next what to do. And this is the small code what I have written here, and I will explain you this code. This is very much important. From this code itself, we will be trying to analyze the various poles and the further analysis. The most important things here are required as omega n. There are two types of omegas I have considered. Considered. You can either if you want to see the response for the series of omega n, you can keep this one and you can comment out this one by placing a percentage symbol here. Or if you want to see only the response of a system for when there is a single omega, then you have to comment out this one. I intentionally kept both of them uncommented. So whatever you want, you can keep it. Suppose if you want to see for various omega values, omega equal to 0, 100, this 100 is the interval, 200, 300, 400, 500, up to 1000. So if you could able to do, if you could able to, see, if you want to see various, if you want to see various responses because of the from various omega n, then you had to use this command. Otherwise, only for single omega n, you can do this. And the damping ratio, I have considered a zeta equal to 1.1. So this is an overdamped case. And since this is an overdamped case, the pole locations will be on the left. If the poles will be real, and they are the distinct. That's what we have seen, and they are placed on the left of a plane, and both are separated by some distance. And this is the formula for the damped frequency omega d, that is omega into square root of 1 minus zeta square. So this beta we are not using because we are not considering about, we are not bothered about this rise time. As I told, our focus is only on the two parameters, the settling time and the peak overshoot. So now what I'm doing here is settling time is 4 by zeta into omega n. This is the dot division. This dot division is because if I consider this omega n as a vector, that means 0 is to 100 is to 1000. To satisfy the dimensions, we have to use this dot division. And this is the settling time formula. So settling time is 4 by zeta omega n. That is the same thing. And this is the peak overshoot, and which is nothing but e to the power of minus pi zeta by square root of 1 minus zeta square. This is the standard formula. So this is the peak overshoot. And this is the peak time, though this is not required, but still I just can pi by omega d, where omega d you can damp frequency, you can get it from there. So now the pole locations, the formula what we have seen, What is the pole location? Minus zeta omega n plus or minus, you can see the plus or minus omega n into square root of zeta square minus 1. This is my pole location. So if you see, if you remember the pole location, that's what I told, that second order, whatever the derivation we are going to derive is very much important. So the pole locations are minus omega n zeta plus or minus 1. For the pole 1 it will be plus, for this another pole it is a minus omega n into square root of zeta square minus 1. This is from the standard formula. Okay, and then better I will go out of this mode. And then what I'm doing here is, once these poles are you can able to find, this display will just display these things just for the fine, for the nice plots. And this display, what I want to display the variables omega n, and the next one is the settling time, and the pole 1 and pole 2. Now if I run this tiny piece of code, which I will share with you, and here I am using this option omega n because I want to see the response. I want to see the complete response of the system when the omega varies from 0 to 1000 with an interval of 100. If I run this code, so you can see that for various values of omegas, different settling times, the pole locations you can see here. So if I go to the next slide, which will, yeah, these are the results. If you run this tiny piece of code, you will be getting different results. So this is the omega n, only the omega n has been given. And one thing you have to remember, that the peak overshoot is fixed because we are fixing the zeta. We are fixing the damping ratio. We fix the damping ratio at 1.1. So because the peak overshoot only depends upon the damping ratio, so the performance of the system will not change. The peak overshoot will not change. And we are aware that the damping ratio for this particular system, since it is a peak overshoot, for this overdamped system, there will not be any peak overshoot. So there is no point in analyzing the peak overshoot. If the damping is fixed and it is critically damped, that means sorry, it is overdamped. If the zeta is greater than 1, then obviously there will not be any peak overshoot, and hence there is no need in discussing, this aspect. So you can see the important thing here is, as the omega n keeps on increasing, if you see the omega, please listen carefully. If you see, if this omega n keeps on increasing, the settling time is decreasing. Why? Because if you see our analytical expression for the settling time is 4 by zeta omega n. So in a way, settling time is inversely proportional to the zeta. Sorry, inversely proportional to the zeta as well as inversely proportional to the omega n. Since zeta is fixed there, we are varying omega n, and since settling time is inversely proportional to the omega n, as you keep on increasing the omega n value, the settling time will decrease. Okay, so let's see from this particular. So this is my settling time, 4 by zeta omega n. So this is omega n. Okay, there is a typo here. So since zeta we are fixing, we fixed the zeta at 1.1. So what is happening here is, if I keep on increasing this omega n, since it is in the denominator and hence inversely proportional, assuming that this zeta is constant and 4 is also constant. So as you keep on increasing this omega n, the natural frequency, and hence my settling time will keep on reducing. So my system will become fast. So let's see. So let's see what to do with this thing. So this is the what analysis you can see. So we will see next the poles, how the poles are affecting. You can see once again I'm repeating, as the omega is increasing, the settling time is inversely proportional to omega by keeping the damping ratio constant. So that's why you can see that settling time is reducing. And the corresponding, since omega n is known to us and zeta n is also known to us, we know that we have seen that if you know the zeta and omega n, you can easily find the poles minus zeta omega n plus or minus root over 1 minus zeta square or so on. So this is standard formula. So you can see that when this omega n is 100 and zeta what we have selected as 1.1, the corresponding poles are minus 64 and minus 150. So as the omega is increasing, you can see that the corresponding poles values are also increasing. So once again I am telling, if omega n is increasing in this order, since the settling time is inversely proportional, settling time will keep on reducing and the poles locations are moving farther and farther to the from the imaginary axis. And since this is a critically damped system, there will not be any imaginary. So yesterday I was telling you, yesterday I told you, and the day before yesterday also I discussed what is the, as you keep on, why we choose minus 1000, minus 2000 and so on. So here is the answer. If I choose one pole as minus 650 and the another pole as minus 1500 approximately, then my settling time will be 0.003. If you want further lesser settling time, let's say maybe 1 microsecond or or so on. So what we have to do is you have to change this value. If you are changing this omega n, then the poles locations will move further to the left hand side. So instead of minus 640, it can become minus 6000 or so on. So that is good thing. It will make your system very fast. But the thing is, the gain pole placement K value will be very high. If the pole placement gain value is very high, that means your actuator needs more power to provide that kind of input to the plant. And again, if the poles are very far away, if the poles are very far away from the imaginary axis, settling time will be very slow, system will be very fast, but the more bandwidth, the bandwidth of the closed loop system will be very large. So that means you are giving the chance for high frequency noise phenomena to enter into your system. So that's why you had to judicially choose the corresponding values of the poles in such a way that it should cater both the time domain as well as the frequency domain specifications. So this is about the selection of the poles location based upon the standard second order the response what we have selected. We fixed the the damping factor, assuming that we don't want the overshoot for the particular system, and then we have done the reverse engineering by varying the omega value to see the corresponding settling time, and for the corresponding settling time, what is the poles required. So as a control engineer, if the settling time is given to you, let us assume only the settling time is given. Your desired specification is you should have some amount of settling time, and the peak overshoot is 0. Then based upon this, whatever you are seeing here, if you want 0.03, you select this pole. If you want further smaller, you select this pole. If you want further smaller, you can select this pole. So this is the way to select the various pole locations for the pole placement controller. So these poles will dictate the closed loop performance. Okay. So this is the procedure what I have developed for the desired pole selection. The summary, whatever we have discussed till now. First, fix the damping factor. In our case, we fixed zeta at 1.1. So this is slightly overdamped system, slightly overdamped system. Because if zeta equal to 1, we call it as a critically damped system. This is slightly overdamped system. This selection of zeta ensures zero peak overshoot. So this is quite, from the time domain response, we can always see that, if we select this particular zeta, then there will not be any peak overshoot. And the next step is vary the natural frequency to get the desired settling time. So that's what we have done. We have varied from the interval of 0 to 1000. This is just for you to show, how the settling time is varying with respect to the omega. If you want much more less settling time, or if you want the faster response, then you can increase the omega and beyond 1000 as well. You can keep 10,000, you can keep 1 lakh, 10 lakh, 100 lakhs, 1000 lakhs, and so on. So based upon the required settling time, select the natural frequency accordingly. So so if you so so based upon the settling time, whatever is your desired one, you select the corresponding natural frequency from the first part. And once if the natural frequency what you have selected, then these are the two poles. Since zeta is fixed, we know the zeta 1.1, and based upon the settling time, we are selecting this omega n. So these two, if they are known, so they are my desired pole locations. So this is the way to find the desired pole location. I was telling from the last classes that how to get the desired pole location. How some people have yesterday in the feedback also mentioned that it is not clear. I hope now it is clear. But I want you to explore this particular aspect. So further, I will show you in terms of the results as well what is happening. So I have plotted the two plots. The first plot is the pole in the x-axis is the pole 1 location and y-axis is pole 2 location. You can see that the relationship between the pole 1 and pole 2 is linear. This is quite obvious because if you see that the pole locations, the real part is the same and the imaginary part is also the complex conjugate. So hence, if you plot the pole 1 with respect to the pole 2, you will get the linear plot. The second thing is what I have seen here is pole locations and the settling time. So this is the what I can say that a set of poles. Suppose these two are the poles. You can see that these poles corresponding to around minus 150, and this is for the first case or even the last case. Whatever we can see that one. And this is around. You can see that this is around 300. So one pole is around minus 50 and the other pole is around 300 plus, which gives us the settling time of 0.36. This we can see from here. You can see that one pole is minus 64 and minus 155, and it gives the corresponding settling time as 0.36 and so on. So that's what. So this is the second set of poles for the corresponding omega, and this is the third set of poles. This is the 4, 5, 6, 7, whatever the 10 sets of poles. So you can see that as the pole locations are going farther away from the imaginary axis, or in other words, as the magnitude of or the absolute values of the poles are increasing, then your settling time is coming down. You can see that the settling time is drastically reduced from 0.04 to 0.00 maybe 3 or so on. So this tells about that as we keep on placing the closed loop poles farther away from the imaginary axis, this will always ensure that your closed loop system will be much faster than than if the poles are near to the imaginary axis. So this is what I would like to say from this thing. This is the how one has to design a practical, the desired pole location for a pole placement controller. So it is not that I have randomly selected minus 1000, minus 2000, or minus 3000. So the philosophy behind selection of those particular desired poles is the analysis what we have discussed now. So a note on desired pole selections. So the above mentioned procedure will only yield approximate desired specifications. The reason why we are not getting the exact desired specifications, although we can say that whatever if you use this one, you should exactly get this one. Up to certain extent you will get it, the similar one, but not the 100% accurate. The reason why, because whatever the formula we have derived from this 4 by zeta omega n and e to the power of minus 5 zeta by omega d into pi. So these two formula we have used to derive our pole location. But for the practical purposes, these are only the approximated or the analytical value. This is not the true sense 100%, this formula, whatever you have seen here, they are not the 100% true value. Because while deriving these things, I have not gone for the derivation. We have assumed certain assumptions, and then we have come up with this formula. So this is not exactly settling time. It's not equal to. It is approximately equal to 4 by zeta omega. So that's why the reason here is the reason why we are not why not getting the exact desired. We will not get the exact desired specification because we have used the approximate or analytical settling time formula 4 by zeta omega 1. This is why we have selected 4 by zeta omega n, because it is quite simple and linear. If you exactly derive this one, then there will be a very big expression for the settling time, which will have lots of non-linear terms and other things. So that will give the exact response. However, if you want to calculate that big expression, then it will take more time. Computationally, it will be more intense. So based on the problem at hand, this desired pole location can further be found. So that's what I would like to say from this one. So the code, whatever I have shown you, if you run this particular code, whatever I have shown you, assuming that I had commented out this single one, then it will show you all these values, and it will show these plots as well. However, if suppose for example I am only interested to, I will say that 0.003 is not the desired one, or 3 microseconds is not 3 milliseconds is not the one. I want further smaller. So what I will do is I will comment out this one. What I have to do here, I will uncomment this one, and I will keep on changing this particular value omega n to very large. And if I run this one, only one value it will become. So it will show you, because there is only one value. So you can see that omega n is 1E5, that means 1 into 10 to the power of 5, very large. You can see that the settling time has drastically come down. Since the settling time has drastically come down to the order of 10 to the power of -5, the pole locations what you are seeing is much more farther away from the imaginary axis. So now what you have to do here is to get the actual feel of the selection of the pole placement controller or whatever we have discussed. I would like you to go through this particular code. This code is already known to you. This code is already known to you. So what you have to do here is, these are the desired pole locations. So I have selected the first case, -65 and -155. You can see that -65 and -155. So what you have to do here is, in this particular code, you keep on changing. The first you keep this value and obtain the step response. And from the step response, so the corresponding value of m you write down, corresponding value of pole. For the first case, it is -65 and -155. And from the plot, and from the DC motor plot, if you run this particular code, you'll be getting the step response. From the step response of this DC motor, you try to find what is the settling time and rise time. Now your task is write down all the omega n's from this one, from this particular table, and fill this pole 1, pole 2 locations as well, pole 1 and pole 2. And for each of these to fill this blocks, so what you have to do is you have to keep on changing this poles value. If you're smart enough, you can use the template what I have suggested earlier, omega n. It varies from different intervals of different at different interval, and then you can get the different values of p1 and enhance the step response and other things as well. So however, if you want to do it manually, first keep this P1 as -65 and -155. Run this code. You will be getting the step. This is the step response. If you right click, it will show you the characteristics. From the characteristics, you can select the settling time and hover your mouse, and you can able to get this settling time and rise time. I will run the sample code for you, and I will show you what you have to do. These all things you have already seen, so I will not go into the details into this particular code. What I'm interested is this particular line. So this is the first case. You can see that the first case, minus 65 and minus 155. If I run this code, the plant is controllable. We discussed yesterday what is happening. And then after some time, you'll be getting a step response. Yeah, this is the step response what you got for the unit step. If you want to see the characteristic, right click, and I'm only interested in the settling time. Click the settling time. Again, right click and click the steady state error or the peak overshoot or whatever it may be. I don't rise time. The rise time I have asked and the rise time, and you can see what you are getting. If you hover your mouse and left click here, it will show you the corresponding and you can see that the settling time is 0.0686, and similarly the rise time is 0.0383. So 0.0683, 0.0686 and 0.0383. So you have to fill here 0.06 and 0.03 what you are getting. In the second case, the omega you can take it as whatever the second omega value. For the second omega value, you will be getting, yeah, this is the second case of omega value. Omega value is 200, you have to write 200, and you have to change the poles to minus 128 and minus 311. So that means go back to this code here, and here you keep that poles, different poles, and you just run this code. Again, it will show you some step response. If you right click that step response, and if you see the corresponding settling time and rise time, you can fill that up, this particular table. So like this, you have to, for the all particular things you may have to fill up, and remind you that whatever the settling time what you will be seeing in that particular single table, that settling time will be different from the actual settling time what you are getting. The pattern will follow the same, or there will be very small variations, but it will not be exactly the same 100%, like it will not match 100%. The reason is why what we discussed there, because 4 by zeta omega n is an equivalent of it's just the equivalent uh, formula. It is not the exact formula. So what I will give you is I will give you some 20 minutes of time, and I will share you this PDF. This time I'm not going to share any of the videos, so you have to do on your own. This is nothing. Just copy paste the code, change the pole values, and plot it and see what is happening, and just put it down. So now, since this is a very important topic, if you have any questions, I am ready to take up a couple of questions, and then I will send you this PDF file to work with. Anyone has any questions?
I have a question, sir.
Yes, please.
I have a
Yeah. Please tell your name and your institute, and then you can ask.
I'm Aisha Garga Ali from the Federal Polytechnic, Damaturu, Nigeria. My question is,
yes,
whenever
yes.
I copy and paste the code in the editor, it always gives me an error whenever I run it. It will give me an error, and I will not see any plot.
Okay, so the reason there here is because I am copying the MATLAB code in the PowerPoint and then convert it into the feedback. So that's why whenever you're copying there, you might have to do some small changes. The small changes may be the single quotes. Wherever is the single quotes, if you see that you have to change, because the characters when you are copying from the MATLAB to the another like PDF, or when you are converting, then some of the character changes. If you just change that particular single quotes, or if you remove that quotes wherever this red color, wherever whatever you see, just Just replace it with a single quotes and it will work.
Okay, sir. Thank you.
Yes, you're welcome. So Chindamani Mayappan has asked, what is the time and frequency response and way to use it? So whatever we have discussed till now is the time response only. It is not the frequency response. However, as a control design engineer, one has to satisfy both the time response as well as the frequency domain. So the thing is, whatever the control and plant, whatever you are seeing, like GH is control plant and C is controller. CS into GS, if you plot the Bode plot, and you could able to get the gain margin, phase margin, bandwidth, and several other, several other frequency domain specifications as well. So we have only discussed about the time domain. However, in the frequency domain, there is some correlation between the time domain and the frequency domain as well. So to some of the frequency domain properties, what one want to see is the noise rejections and the bandwidth and the gain margin, the phase margin. So gain margin for the practical systems in general, the gain margin should be greater than 12 dBs, and the phase margin generally they use more than 30 dBs. So when you convert, so this specification, whatever I'm telling you, if it been converted to the time domain specification, it yields to kind of underdamped system, because the phase margin sometimes phase margin equal to 10 into zeta or something like that. If you want the approximately, if you want the phase margin of 60 degrees, then the equivalent damping ratio in the time domain will be the 0.6, which is underdamped, and so on. So, so what you can do here is the time domain and frequency domain need to be analyzed for all the systems to study the frequency, basically to study the noise properties, to study the bandwidth properties, and so on. So those properties you cannot see from the directly, you cannot view from the time domain analysis. However, there is some correlation exist between the time domain and the frequency domain. For example, the peak overshoot in the time domain is equivalent to the resonant peak in the frequency domain, and so on. And the settling time in the time domain, there is some, it is directly correlated to the bandwidth of the frequency domain. Though I spoke about it, but we have not for all the practical equations, one has to select these two. One has to satisfy both the time domain as well as the frequency domain properties. Someone has asked, P1 and P2 has to be changed in each time in programming, or can we write a program values? Yeah, you can write it. The first program what I have shown you, where I'm changing the omega n in the intervals to get the different poles, you can use a similar code. Good morning, sir. In 3 quizzes regarding DC motor, desired poles are given and the sum of the PPC gain has been asked. Please clarify. Okay. So I will clarify this particular doubt. KV SS Rao has asked. So desired pole location. Okay, I will explain through the code, MATLAB code. I have not shared my screen, so let me share my screen now. Okay, so this is the small code, MATLAB code. If I use the desired poles, if you use the desired poles, and this KPPC will give us, if I run this one, let's say if I run this one. So the K underscore PPC is the pole placement gain. So there will be 3 different K underscore PPC. If you see K underscore PPC, yeah, since it is second order session, there will be 2. So the answer here is, if I add these 2 things, so the sum of these gains, so 3987 plus 100, so approximately it is 4100 will be the answer. So that's what I have asked. P. Soumya is asking, sir, the system will be stable unless the value of zeta is less than 1. In that case, do we need any pole placement controller for critically damped condition? Okay, I'm a bit confused. Let me read this one. Sir, the system will be stable unless the value of zeta is less than 1. No, if the zeta is greater than 1 as well, the system will be stable. The system will be stable. If that is called as a overdamped system. The system will be stable irrespective, if
Hello.
zeta is greater than 1 as well.
Sir, I'm Soumya.
Yeah. Yes.
My question is, the system will always be stable when it is critically damped. So if it is less, then only we need to see for the location of the poles, because there is a possibility that it will go to the right hand side. So in that case only we'll need adjustment of poles, no sir.
No, even if the critical time system, if there is no overshoot, but the system response can be slow as well. You know,
And
for this particular system, for the system
if it
what
is
we have
only sluggish or slow, then we'll be
sorry,
going for that. If it is slow
your
or sluggish, am I audible?
yes, you are audible.
If the system's response is slow and sluggish, then we'll be going for adjustment. But in predominantly, if it is on the right hand side, we'll be going for the adjustment and pole placement control, sir.
There
Hope
are
I am.
two reasons why we designed the control system. The first one is to stabilize the system. If the poles are on the right half of S plate, we try to push the particular open loop right hand side poles to the left hand side. That is the first case. The second case is even if your system is stable, then also the controller is required. Again, due to the two reasons, even if the system is stable, for the two particular reasons, you need the feedback controller. The first reason is if the system is slow or it is not satisfying the desired specification, you need the control. The second case is if your system is uncertain. If your system is uncertain, then whatever the already existing controller will not work. So for that one, you need some kind of feedback mechanism to handle that uncertainty, because the system is not going to operate, assuming that all the parameters are constant and it is not affected by any kind of external disturbances or so on, or the parameters that is in the realistic case. Open loop systems will hardly will, if there is no uncertainty, if everything is perfect, everything is nominal, yes, it is not required, but that is not the case of the realistic system. So that is my answer.
Thank you, sir. Thank you, sir.
So I will be sharing the file with you. You please do that DC motor pole placement controller design. So I just sent that one, the complete file to you, and you can go through that one. So we'll meet at around 10:20 or 10, around 10:20. By then you try to fill that table, and then we'll see what to do next.
హలో
Okay, any of you have completed the work what was assigned to you?
Almost, sir.
Almost. Very good. So how is the response? The settling time what you are getting from the theoretical calculations, what I have shown in the slide, and the actual one, is the pattern is matching?
It's matching, sir.
It's matching. Okay. So that is it make sense? The selection of poles, what we discussed today. Okay. Anyone else? Could you please put in the chat box if you don't want to answer? Okay. So no worries. So we will go back to in process. Fine. Fine. Okay. It might
Hello.
take a bit time, but yeah. Hello.
So this is Parthiban.
Yeah. Hi. Hi,
Sir,
Fatima.
when I run the first code, that is, you explained that how to find that different poles for the different natural frequencies, varying from 0 to 1000 with the zeta value
Yes.
1.1.
Yes.
But in the slide, there are some variation in settling times. From starting from infinity, then 0.03 something, and it extends up to
Yes.
0.003.
Yes.
But
Yes.
in my case, when I run in MATLAB, I got
Hmm.
approximately equal values for poles,
Fine.
but
Yeah.
I got zero settling times in all
No.
inputs.
No. Actually, yeah. I know what is happening. Into 10 to the power, something will be there. If you say you had to
Yes,
change the
yes,
format,
yes,
you type
yes.
format short G. It will give you the desired values in the desired format. You just type format short G, format
Format
space
short. Okay, sir.
short G short G, short G,
For,
and then again if you run, you can able to everything is there. Only thing is your visualization is not good.
okay, sir. Format space short space G, right, sir?
Not no space in between short G.
Short G. Okay, sir.
Yeah, yeah,
Okay, now I will try, sir.
yeah. Okay, guys. So we will be winding up our session in another 10 minutes. So let's start our discussion.
Hello, sir. Now I got it, sir.
Yeah, hello. You got it right.
Thank you,
Yeah,
sir.
that was the
Yes, sir.
mistake.
Thank you.
What you are doing. Yeah.
Okay. Okay. Thank you, sir.
Okay. Okay. So let's start our discussion on. I will be sharing my screen now. To okay. So actually, I want you to plot the omega and the settling time as well for this particular DC motor, and the pole locations and the settling time as well. So what I want to see is as the omega is increasing, the settling time should reduce. And as the poles are getting farther to the left half of S plane, then settling time should also, it should be very fast. That means settling time should reduce. So these two plots, if any of you have plotted, that would be good. Otherwise, you can do in your leisure time. So the next thing is a single machine infinite bus system. This you can take it as a homework. I will not put much stress on this one. So that this is the reference from this paper I have selected. So the only thing is, again, I'm not putting much stress on this one. So what you have to do is you have to design the PID controller such that if there is some variations here, the change in frequency or the change in speed should be equal to 0. So this is what we need. So you can see this more details in this paper. If you couldn't able to get this paper, I will share this reference in the WhatsApp group. So now we are ending towards the summary. The summary of this particular workshop is we have started our discussions on fundamentals of control systems. We started with various examples, and Professor Anup Jain, he has addressed us for 10 to 15 minutes on the day one, and he has also shown us various applications and his multi-agent work as well, the synchronization of the multi-agent work. And then we have discussed the open loop and closed loop controls and the requirement with some realistic example, the open loop as well as closed loop. And then we have seen the theoretical aspects of proportional control alone and the proportional integral control and PID controller design. And more specifically, we have, if you see, inherently we have done the 4 different case studies, and you have already done the coding along with me. The first one, we have started with a simple transfer function with inherent integral action. In that particular example, what we have seen that only the proportional controller can able to deal with that one, and it is not required to use the integral because the plant itself has inherent integral action. In the next case, what we did is that integral action we have removed by adding a constant in the denominator, so that removes the inherent integral action, and we have seen that proportional controller cannot able to deal on its own. So we have gone for the another one which is called as PI controller, and the integral control has a caliber to remove the steady state error or to make the steady state error to 0. However, the main purpose of the proportional is to improve the rise time, integral to improve to minimize or to make the steady state error 0, and the derivative to improve the overall stability. But the caution here is that you should not use the derivative unless it is required for the practical reasons what we discussed due to the noise amplification and so on. And we have seen for the RLC circuit as well, we have derived and we have find out the corresponding PPID, PPI controller design as well. And then the DC motor, and then finally the buck converter. Yesterday we have seen the buck converter. And we have seen the importance of the proportional, integral, and PID controllers. And then we have seen how to design the PID controller in 1 minute, and that is called as an auto tuning. And then we have gone for the pole placement controller without integral action and with integral action as well. So we have seen when we are not using the integral action, the steady state error is not going to 0. However, if we augment the system with the error derivative, then we could able to track, we could able to ensure that the error will go to 0, and hence the steady state error will be 0. And then today we have discussed a very important point, a very important topic, a critical analysis of pole placement controller. How to select the pole and what is its implications on the settling time, the implications on if we select different values of omegas of natural frequency and the different values of damping factor, and how the system responds and how it will affect. So this is the overall summary of this one. I can take a couple of quick questions because we have only 3 or 4 minutes, and then we'll start the valedictory. If you have anything to ask, now the forum is open for the discussion. Though in between also I was answering several questions, but if you have anything. So day 3 Q sum of PPC, I did not get it. I already just discussed. I discussed that one. I don't know whether Harshita, you were there. I discussed this just before 20 minutes, and I have answered someone else. I think KVSS Rao has asked this question, and I have responded to that one before half an hour. I think you were not there at the time. But okay, now it is resolved. Okay, Muhammad Adil Sheikh, now it is resolved. Yes, so if you have any queries, I'm here for another couple of minutes, and then we'll start the formal valedictory function. Sir, can you explain format short G function? It is not the function, it is just the display. There are various ways to display, the whatever the numbers, format long, short, format long E, short E. So that will tell you, how many decimal places you want to display in the MATLAB and which format you want to display. So the best thing is you just to type help format. It will show you at least 15 to 20 such thing. And short G is one such thing which will accurately display I think until 5 or 6 decimal places. I will show you that one if you want to clear how it works. If you just put this help format, then there are so many things here. You can see that there are at least short up to 5 digits, long up to 7 digits, short E 14.5 digits, long E 14.5 digits. So if you want to display till 5 digits, then because that's what we need. We don't need more than that one. So that's what I'm using, that short J. If you want to display it till 7 digits, then you can use this long G and so on. That is my answer to Ramesh.
Hello. Hello.
Yeah, hello.
Good morning,
Yeah.
sir. Sir,
Good
yesterday
morning.
buck converter with the closed loop control response got a spike.
Yeah.
How to reduce, sir?
Sorry.
Is it audible, sir? Yesterday,
Yeah. Please repeat
buck
your question.
converter with
Yeah.
closed loop control. Yesterday,
Yeah.
buck converter with the closed loop control response got a spike.
Hmm.
Based on
Spike.
yesterday question.
What do you mean by spike?
Yesterday buck converter response.
Yeah.
Buck converter with the closed loop control response got a spike. Small spike, small dip got it.
Yes. Yeah.
After that, it came to
So
stable.
Yes. That is called
How
as an
to reduce
overshoot.
that
Yeah.
spike?
That's what I'm
Okay.
telling you from the past 5 days. That is the overshoot. How to reduce the overshoot? It has already been discussed in several times. So now you
Yes,
have to
sir,
do the practice.
Okay. Adjustment of PID control, sir.
Yes, of course. Of course.
Okay.
I will take the last question now and then I will start the valedictory. I hope people don't have any questions. So first of all, I would like to thank you formally all the participants for being patient for these 5 days and listening my lectures
Hello,
carefully.
sir. Hello, sir.
Yeah, hello.
Hello. Sorry
Yeah,
for the
hi.
disturbance.
Yeah, please
Once
tell.
again, Parthiban. Sir,
Yeah, hi.
when I run that code for getting the step response, I got an error, sir. That is undefined function or variable. It coming again and again. Initially, it comes as undefined variable p1, and then the third code for getting the step response. So I go to the first code and change it as I changed pole underscore one as p1 because in that it is developed as assigned as pole underscore one. But in the last code it is defined as p1. I changed this as p1. But once again it is coming that is undefined function or variable. I'm not getting the output.
What is that undefined variable? There will be the
First
complete
time it comes as p1. Now it comes as a.
A, capital A or what?
Capital
Small
A.
a. No,
Capital
it
A,
should be
sir.
defined. No, it is defined. If you run that code exactly, you'll get it because exactly the same code I have given to you. What I am running. Because it has been
Uh,
already explained in the PDF file. If you see on the left side, that A matrix has been given.
That is a parameter. There is a parameter file. I have run that, and also I have run that first code also. After that, I
No,
go for third and
you don't need any first code, sir. If you just want to run, you just run this DC motor code itself. It is
okay, sir.
self-contained code. You don't have to run any other code. It is a self-contained code.
But it is not running. I don't know. It is
I
a
mean,
underscore
there is,
PPC is equal to
sorry.
that code alone is enough, sir. That is, it starts with the statement k underscore pole placement control. PPC is equal to place of a comma b
Yeah,
comma within the scope.
this is the same code, sir. This part 1 and part 2 is the same code. You have to keep in the same file. I don't know whether you have kept in the same file or not. The left side and
Oh,
the
that
right
is the
side.
problem.
Yeah,
Okay.
the right side is the extension of the left side. That's why it is not running. You have to keep both in the same file. Since the code
It's
is very
my
big, I have
mistake.
created for this. Yeah.
Okay.
Okay.
Okay, sir. I understand. Thank you.
Okay. Yeah. Okay, guys. So thank you very much for being patient with me for these 5 days, and I'm sure your learning was good, and I also ensured that you should be on your toes. So for the validity function, we have the chief guest with us is Professor M. Venkateshwar Rao, who is a professor and head of JNU Anantapur College of Engineering, Kalikiri. And he is a very good friend of mine, and we know each other from the past 15 years. And he was associated with the GMR Institute at various academic and admin positions. And now currently he's a professor and head at JNT Anantapur Military. And his expertise is in power systems. He has done his bachelor's from NPKR Institute Wakadu and MTech from JNTU and PhD from JNTU Kakinada. And he has extensively worked in the power system of controller, power system designs, and specifically the PAX devices and so on. So welcome you, sir, for accepting our invitation in a short time to be a chief guest of this particular event. So it is over to you, sir. Please address our participants. To brief you, around 130 participants have registered for this, successfully registered for this one from around 19 states, and participants are from Nigeria and Saudi Arabia as well. So overall, it was a very good. My personal experience is that it went very fine, and the response from the participants were very good. So that's what I was expecting. In general, the FDPs or SDPs, just the people just come and listen and go. It's not like that. So the input from the participants were also very good. So they also continuously with me. They also worked, and we have lots of exchanges as far as the codes are concerned and their queries and other things. 24/7 we were working, and it was quite fruitful. It's over to you, Professor. Your voice is not
Okay.
audible, sir.
Thank you, Mr.
Yeah,
Bharat.
yeah.
Voice is
Yeah,
not audible. Is it
yeah, it is
okay?
audible now. Yeah, it is
Yeah.
better now. Yeah.
Okay. I think I'm audible. I'm also visible.
Yes. Both.
Yeah. Yeah. First of all, good morning, one and all. And especially the resource person, who is very good friend of mine, Professor Bharani Chandra Kumar. And on the other hand, I would like to say that the way how it was went on, I was with you in the group from the past 15-20 minutes, and the way you have connected with the resource person is very good. And to my knowledge, I asked my students also to join for this SDP, and most probably, I think around 20 to 25 are online right now. Maybe more than that, or plus or minus. Anyway, very good morning to all once again, and I was very happy to join with GMRIT once again, especially Professor Bharani. And I'll come to the content later, but I'll try to speak about Professor Bharani for 1 or 2 minutes. And with regard to Bharani, we were very good friends from past 15 years. In fact, when I was HOD, he has joined as a faculty in the GMRIT. He has submitted the joining report, everything to me only when I was HOD there. And from the day one, I observed him that he was workaholic and professionally connected with all, and personally also very jovial person. And he has a very good habit, like he won't keep the knowledge with him. He always try to share with the people at all levels, maybe professional level or peer group or students or anybody. In fact, whatever he knows, he used to share with the people, and that was a very good sign for a person who is professionally working as a faculty. Why? Because if you know something, if you can't share with the others, that's useless. That's going to dead there itself. But he is a continuous learner, so that is the reason why he could able to utilize or make best out of this COVID time or critical time. To my knowledge, from the past 1.5 to 2 months, he was not having a proper sleep. Also, he has conducted many FDPs, SDPs for the faculty, students, and also online connectivity, YouTube connectivity, and also conducting alumni meets, not many more. So, what I would like to inform the present participants that try to be, don't get disconnected immediately with him. You try to pamper him. You try to be behind him so that he will be useful for you, even if you, whenever you go to any PG level or PhD level or anywhere. If at all, if you choose your career in the control system, especially, he is a very good resource person through, I can say, even in many countries he has a close contact with the peer group, so he can make the things done. But at the same time, don't think that 100% you can't rely, or you can't depend on him. You have to do 99%. He will add 1% so that that will become 100% at your level. So that's why I advise you, if at all, if you have anything, you discuss with him. He may provide his mail ID, so whenever he feels time, he will be responding to you and try to learn the things to the possible extent. And that's with regard to Bharani. And in fact, I thank GMRIT also to provide the opportunity to get connect with GMRIT banner once again. And since I was with GMRIT for around 2 decades, I can't I can't leave GMRIT. It is in my blood, and I'm here because of GMRIT only. For the past 20 years, whatever the things I learned, that was made me to be seated here. That was made me to be as a chief guest for today's event also. And with regard to the content, I think he delivers to his best. And at the same time, control system is one of the important subject which links to all the subjects like power systems, power electronics, and many more subjects. So wherever you go, there will be a systems will have a error, and how you overcome that error is the basic thing. And if that error can be minimized, or if that error can be possible to reduce, then obviously the result will be as per the expectation. That's what the world is looking for, how to minimize the error. So in fact, it's an app title for the FDP or SDP, whatever you call, and having a hands-on experience with the content. And also all the controller, I understood that all the controller designs were explained, PI, PID, and with regard to the MATLAB and Simulink approach. And also he has taken some case studies like single machine infinite bus, which you can connect it to even power system aspects also. And also at the end, some pole placement techniques and all. So in fact, the 5 days, whatever you have spent, maybe you might have spent around 15, 20 minutes, 20 hours of time. And that was, I can say that that was one of the best time you have spent in your life. So I hope this is going to be a seed for you to think in the line of research as well as your professional growth. And I appreciate Bharani to come forward to this kind of the lectures or FDP. And since I am elderly person, I bless you to give much more kind of academically based activity, so that the students community will get benefited, and also the peer group will get benefited, and in turn it will be a benefit for the country, in turn it will be a benefit for the world, as how we are all looking for someone to get ready with the vaccination out of the 130 countries. So if one person gets clicked, then obviously that is a big boost for the entire world. Similarly, if one of you become a stalwart of in this field, that will be useful for the society. So thank you once again for giving me the opportunity. So that's all from my side, and all the very best.
Thank you, Professor, for the wonderful, fantastic, valedictory speech. Now the session is open for the feedback. You can give your voiceover feedback if you have anything feedback for this particular session. It could be anything.
1 second, sorry to disturb you. Can I leave?
Yes, sir. Yes, sir. Yes, sir. Yeah, sure.
Okay.
If you want, you can stay. Otherwise, no problem. Thank you. Thank you very much.
Okay.
Yeah.
Okay. Thank you.
Hey, thank you. Thank you. Participant, do you have anything to say?
Good morning, sir. I'm
Good morning.
Sailaja from Vasavi College of Engineering.
Hi, Sailaja. Yeah.
Sir, am I audible, sir?
Yes, you are. You are audible. Yeah.
Sir, actually, I attended a faculty development program, and I gave the feedback that in one of the quizzes that you have sent, that sir, please go a little slow so that everyone can understand. After a few days of attending FDP, I understood that you clearly know who are the audience you are targeting. And then I understood, because and one more quiz feedback I gave, that whatever the topics that you are covering are above my level. Then when you have shared the link for this SDP, I thought, even though it is for students, let me learn. So I joined this SDP also, and I'm thankful to you that you have accepted my application and given this opportunity to attend. And one more thing I would like to appreciate, sir, that your way of teaching is very, very good, sir. And the modulation of the voice, you never said anything harsh to any student, even though they are asking very, very basic questions. And I can certainly say that you have given a good confidence to me that I can also do something on control system. So actually, the word that student development or the faculty development you have developed, sir. Thanks a lot, sir. Thank you, sir.
Thank you, Sailaja. Thank you for the compliments. And it's good that you are learning something out of this HTP or FDP. That is more important.
Thank you, sir.
Thank you.
Sir, good morning, sir.
Good morning.
Sir, this is Ramesh Babu from St. Anne's Engineering College, Chirala, sir, Andhra Pradesh.
Hi, Ramesh.
So,
yeah, hi.
Yeah. Good morning, sir. It's really what I can say, that your teaching is like a addiction to us, sir. Really. So unfortunately, I missed the controls 1.0 because of my scheduled classes to the students. But I attended 2.0 and SDP also. Really, being a teacher, really, I'm feeling like very privileged to attend to your classes. Like the way how you are teaching and how you are sharing the knowledge. See, some of the very, very important techniques which can take years and years together, but you are giving in a seconds. Really, I never found this kind of a faculty member anywhere who can share whatever he knows, sir. First thing. And second one is availability is really, it's awesome, sir. 24/7, you are awesome, because I have sent many mails to you regarding whenever I got doubt, and your reply is like at the speed of light, I can say. Right? And next one is the organizing is really, I told in the last 2.0 also, sir. See, you are a single man. organizing these many tasks. Really, it's a very very difficult task, and you made it like a one-man army, sir. So really, I'm feeling very happy to attend because I attended one workshop at SV set and 2.0 and this also. So really, I'm feeling very happy, sir. So as far as before attending these workshops, control systems, I'm only 5%. Now I can say that 35% I'm good in control systems. So I'm praying God to provide you good health to serve to the peers, students, faculty, to the society. Thank you very much, sir.
Thank you, Ramesh. So I'm glad that from the 5% you have gone to 35, and I hope soon, very soon, you will be becoming 100% in the control systems as well. Thank you.
Sure, sir. Thank you very much, sir.
Thank you.
Hello, sir.
Hello.
This is Swarthiban from Sedamal Engineering College, Tamil Nadu.
Hi, Parthiban. Hi.
I have already attended your FDPs 1.0, 2.0, and now this SDP also.
Yes.
What to say? That is wordless I am. But actually, really, your lectures are mesmerizing me, sir. Actually, I am afraid of control systems. Actually, I am also from electrical background. I studied when I was in UG. I studied. After that, I am completely out of date with control systems. But now I am doing my research in controller design for unmanned aerial vehicles. So that's what I again just want to know control systems. Still, when I attended the FTP 2.0, I am having some problem in understanding control engineering and all. But after attending this SDP, I got the confidence that even I can learn control systems and all. Now I got some idea in control systems. So
Very
really,
good,
it's
very good.
very great, sir. Your lectures are simply superb, sir. Very easy to understand.
Thank you. Thank
But
you.
my
So,
one humble request, sir.
Please. Yes.
Just like NPTEL video series,
Yeah.
you are also taking classes control systems in your colleges, right, sir?
Yes.
If you please
Yeah.
upload such videos in YouTube like channels,
Sure,
if time
definitely.
permits, please upload it, sir. Then it will be very useful for people like me.
Definitely. I'll be going for that one. I'm thinking something big. Maybe I may be going for Udemy lecturer, but I don't know when and how it will materialize. But thank you very much for the suggestion. And
Please
what I can
do,
say is,
please have this WhatsApp group always alive, sir. If,
I will keep
whenever
it
you have
alive.
doubts.
Yeah, sure.
Okay.
Definitely.
Thank you so much.
And
Thank
I
you, sir.
hope you will soon design the unmanned UAVs controller in a very nicer way, and it should
Thank you so much, sir. Thank you so much, sir.
give the stable response. Yes.
Okay, sir. If I have any doubt, then may I ask you, sir, regarding the design of controllers?
Yeah, sure. At any time. At any time.
Thank you,
Yeah.
sir.
Yes.
Good morning, sir. I'm Soumya, and
Hi. Good morning.
I'm pursuing my PhD right now. I've worked as a faculty uh, and even taught control systems. But there were so many doubts that have been clarified, and you have given such a wonderful explanation of each and everything. I really appreciate that and the patience that you have in giving every detail. It's really nice, sir. Thank you very much for giving us very informative and very useful that are needed in our research and all the work. Thank you so much.
Thank you. Thank you, Soumya. Thank you.
Sir, good afternoon, sir. This is Apara from Venkateshwara College of Engineering. I think
Good
time is
afternoon.
very less. Good afternoon, sir. Participants gave already feedback regarding this program SDP, and though it's on paper 10 hours, even if you go for 50 hours or 100 hours through the textbooks, still some concepts will be hide. So that's why This 10 hours program SDP helped us like 100 hours or 200 hours. Like coming to that, every faculty will do their job or responsibilities, but we are doing service to the whole world, because whenever concepts are clear, people can do their work on their own. Only the thing is you have lightened all the hidden concepts. If I say legend of control systems, it may be lesser. So people are using from 1.0 itself, people are using call you as a bahubali of a control systems. Thank you, sir. Thank you for such a wonderful SDP and giving me this opportunity. Thank you, sir.
Yeah, thank you, Mr. Apparao. And actually, my intention was whatever I have learned in the past 2 decades. I'm working in this control system in area from the last 1.5 to 2 decades. Yeah, almost 17 years in this field, and I got a good opportunity to work with some of the best in the world, not only in India, in the world, some of the best, the top control engineers, the top control researchers. So whatever I have learned during this 17 years or 2 decades, just I was trying to simplify the things, because I myself have struggled during my early days, because of the lack of guidance. And so my intention is to, whatever I suffered from past, during my initial stages of research, nobody should suffer, and they could start, there is no point in working on some area for past 1.5 year when it is possible to learn within 5 minutes or 10 minutes. So that was my purpose, to make the students, faculty, researchers, everyone. So at least till now, around 500 plus faculty researchers from various countries, and in India as well, NITs, IITs, and universities, institutes, several participants have joined, and the still I'll be doing the same. I'll be continuing the sharing my knowledge to all the uh, research community. So whatever I have done, and as I told in the last FDP, it took 15 years for me to write a one book on state estimation by Springer, and I'll be sharing all the codes, which I took, at least 10 years to write the codes for that one. I'll be keeping for open for the research community very soon as well. So that's what I would like to do. So that's my contribution to the research community. I learned several things from several people throughout the world. So it is now my chance, whatever the little things I have learned, so I could, if I can pass on to the next generation, or to the people who are working in the control. So that's my actual aim. So that is it from my side. Yeah, that's what I would like to say.
So thank you, sir. Thank you.
Thank you, Apparo sir. Thank you. Yes.
Good morning, sir.
So I think,
I'm
yeah. Hi. Good morning.
Good morning, sir. Myself, I'm Sundar from Manchester College, Eckerla.
Hi, Sundar.
It is very glad to have you, sir, for attending your session. No one of the students like this attended before anyone. This is very helpful to us, to the students, to attend this session. The way you respond, the way you teach is very clean and transparent manner, sir. Love you, and
Thank you.
you have given a lot of stuff to the students. Though so many have doubts, you are cleared in the WhatsApp chat box. So thank you for connecting this session. You are very helpful for this session, and gain a lot of knowledge the way how to simulate the network or draw the network, the way how to explain the network, the way of learning. Everything what you have done is very clear and transparent. Thank you for conducting this session. Thank you, sir.
Yes, thank you. Thank you, guys. Thank you, Sundar. And there was some power issues. Now it is okay, fine. Yeah. Thank you, Sundar. So I'm glad that you learned something. The 10 hours what you spent for this FDP should not go waste. So that is actually my purpose is also, because I give importance to the participant time as well. So It is not that, since you are spending 10 hours, you should take something away from this 10 hours. It's nothing like I generally don't want to waste the participant time. I appreciate all the participants' efforts in, in being with me for the last 5 days, though in between, sometimes I got bit annoyed. The only thing, the things, if somebody is disturbing when I'm delivering the lecture, in either of the ways, maybe due to the net, due to, whatever the reasons, that is the only time I get little bit annoyed. But otherwise, it is fine for me. I can. So everything went fine except one or two couple of times I was a bit annoyed. But apart from that, the things went very smoothly, and I'm very happy with all the participants. Yeah. So one of my request is, all of you, could you please keep your videos on, so that I will take one memorable picture. So just keep it on for 1 minute. That should be fine. All of you. It's my kind
Okay.
request. The 83 people are there. If you don't have any issues, please, all of you, please keep it on for 1 minute. Not
Sir, this pic also you please WhatsApp, sir, if
I will do it,
possible.
sir. I will do it.
Okay, sir.
You can take the screenshot from your view as well, sir. View everyone.
Okay, 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 sir. Okay, sir.
Slowly, people are switching on their video. So I will just wait until everybody switches on their video. Let me take the screenshot. You people also can take the screenshot. If I miss the screenshot, then you can send it to me as well, or you can send it in the group as well. Yes.
How to take the screenshot, sir, on the laptop? Huh? Sorry, please.
There is view everyone will be option will be there. View everyone.
Okay, sir. Okay.
Is it there?
Yeah, view everyone, sir. Okay, sir.
Yeah. Now you can take the screenshot. Please take the screenshot, sir, because I have some difficulty in taking the screenshot. I couldn't able to
Okay,
take
sir.
the
Yeah.
screenshot
How to
properly.
take screenshot? Screenshot
Print screen.
on
Print screen
laptop.
button.
On laptop. Okay, sir. Okay.
Yes. Yeah. Okay, guys. Thank you for keeping your on for a minute. Very much. So now I'd like to end the session here, and I will keep the WhatsApp group open. And as I promise that I will be sharing this here. So this is the link already I shared in the group. So that is the Grand Q's link. So I will be. This is a sharp 12 o'clock, as I promised. I shared it, and it will be open till 12:30 today. So only half an hour will be given. Please don't ask additional time for this one, because I don't want to give as well. So it is my sincere request. Even if your friends, those who are not here, you can pass it on to them as well. I don't mind, but I will, I will close the session at by. I will deactivate this link at 12:30 today. So all the best. Happy control engineers. So if you have any difficulty, or if you want to discuss anything at any time, you can, you can discuss over the WhatsApp group, or you can mail me as well, or you can send me a personal chat as well. But phones generally, I don't, I don't receive. I'm not that much fan in receiving the phone calls, unless if it is emergency. Please call me. Otherwise, generally, I don't pick the calls because of my very busy schedule. If you are facing difficulty in understanding something, or if you really want to talk to me, you are always welcome. Yeah, that's it from my side. So wish you all the best. Have safe stay. So I'm ending this session, and I will activate this link at 12:30. Thank you all. Thank you.
Thank you, sir.
Thank you.